Now that we've got the union, intersection, and complement measures down in terms of set operations, we can talk about some additional information and formulas. One of these is going to be about counting how many things are inside of a set, and another of these is going to be called the De Morgan laws. Then we'll get into some real examples. To count a set, we talk about its cardinality. This is just the number of elements in a set. If I want to talk about the number of elements in the set M, well, that's easy enough. There's 1, 2, 3, 4, 5 people inside the VC math department. This is one of those places where you want to be very careful. This is a lowercase n, and this, despite what it might look like, is trying its best to be an uppercase m. In math, a lot of times we use different letters for different things. So set names have capital letters. The universe, this is being a capital U. And things that are lowercase have different meanings. One of the biggest, not mistakes, but iffy practices, risks, I guess, that I see students take in math is I see people change the capitalization of a letter. So somebody might write this like this, or might write all lowercase, or who knows, uppercase and then lowercase. I think this might be a bit of a pattern recognition issue, and math is very much about pattern recognitions, but you want to be very, very careful that you continue with the letter in the same capitalization that the book does, because we often recycle letters. Different letters mean different things. So this lowercase n here means I'm going to count the number of things in set M, but if I was talking about a capital N, in math, the letter capital N means the numbers 1, 2, 3, 4, 5, 6, 7, and so on. These are called the natural numbers, because they're the ones you can count with, and these are things denoted by capital N. So just be cautious when you're using upper and lower case. It sounds a little bit like a picky thing, but there's actually a reason for me being picky about it. I'm hoping that it won't lead you into mistakes later on when the difference between an upper or lower case is everything. So if I'm counting the number of things in set M, that's great. There's 5 people in the VC math department. I could also count the number of things in set P. There's 2 people in the VC physics department. But what if I want to count the number of things in the 2 of them together? So this gets us to our first sort of set formula. I want to count the number of things in M union P. The number of things in both these sets. Well, what is it full of? It's the numbers of things that are in set M plus the number of things that's going to be in set P. But notice when I'm counting number of things, I don't really want to count Mr. White twice. So it's 1, 2, 3, 4, 5, 6. It's 6 things that I want to get out of this altogether. But if I carry on with what I've got, I'm getting 5 plus 2, which is going to give me 7. I want 1 less than 7. I'm trying to subtract 1. So I want to be subtracting 1, and the way I subtract 1 is I subtract the number of things that's inside the intersection of M and P. I counted Mr. White once here, I counted him once here, so I get rid of him once here, because he's the common ground. And so that's what leads to the subtraction, giving me the answer 6 that we all know is the correct answer for that. In your book, again, it gives you a general formula, and it gives it with A union B is going to be the number of things in A plus the number of things in B minus the number of things in their common ground, the intersection. Again, it's because you counted up all the A stuff, you counted up all the B stuff, and now you get rid of the people you've double counted. In my example, the person double counted was just Mr. White. So we can find out how many people are in the joined sets as a total. So that's one thing that we've got. The other thing that we've got in terms of formulas that we want to use is going to be called the De Morgan laws. These don't use so much union, just union intersection. They also bring the complement, which is our third set operation, into it. So here I have De Morgan's laws. There's two De Morgan's laws, and they deal with parentheses. Now remember, in math, parentheses means you do the inside part first and then do the outside. Here's what the first De Morgan's law says. It says that if I have two sets and I intersect them and then take the complement, that's the same thing as if I took the complement of each of the sets separately and then joined those two things up in union. Let me draw two pictures of Venn diagrams to convince you that this is actually true. Here's set A, here's set A, and here's set B. Now what I'm going to do is I'm going to eventually shade in the color yellow highlight what both of these areas actually are. To get there, I might use some other colors. So first of all, let's talk about what A union B is. A intersection B, this is the intersection one. A intersection B means that my elements have to live in both A and in B, and that means I'm talking about this common ground right here. That's what this is. Well, once I talk about this common ground here, and then take the complement of it, the complement of this is all of the parts outside that common ground there. So if I shade in the complement, because that's the last step that we do, this is part of the complement, this is part of the complement, as well as all this stuff out here. What I've really done then is told you that regions 1, 3, and 4 are part of this A intersection B complement business. Let's go over to this one and then see if I get the same sort of stuff. So first, let's talk about what A complement is. A complement is all the stuff that's outside of A. This is an A, this is an A. So this part here is outside of A, as well as all this. On the other hand, if I talk to you about B complement, what's outside of B? Well, this is outside of B. All this is outside of B. I can't take in any of the things inside of B. So when I join them all both together and union them up, what do I have? Well, I have this squiggled in area, I've got this squiggled in area, and then I certainly have this double squiggled area, which again is regions 1, 3, and 4. You can't apparently do 4. So that tells you those two things are actually equal. And this is a big thing in math. In the previous chapter, we talked about counterexamples. The difference between a counterexample using one type of our logic and then using the other type of logic that we discussed to talk about things that were absolutely true from general rules was that if I was using inductive logic, I could find counterexamples. What we've just done is perhaps your first real example of deductive logic. I've understood the general thing. This wasn't for any set A and B. This was for a particular set A and B, like my M and P that I was talking about. I wasn't using those. I was using any A and any B. This was anything using my general Venn diagram shape. Because this was going from the general rule, I know that this will always work for any particular sets that I'm working with. So that's the first De Morgan law. The second De Morgan law is just the same thing, except instead of doing intersection and then complement, I do union and then complement. And when I'm doing union and then complement, De Morgan's law says this. It's the same thing as taking the complement of each of the pieces separately, but then instead of union, I'm intersecting. Notice the pattern. I have intersection of two things, and I'm talking about complement. So I change the complement of the two things, and I switch this from intersection to union. Down here, I'm talking about union, and I switch from union to intersection. So that's what we're looking at here. Again, I can shade in areas of the Venn diagrams to convince you that this is always true, no matter what particular sets I'm talking about. So here's set A and set A. And let's talk about set B and set B inside my universes. Well, if I'm talking about A union B, if I shade in that area, that's all of this, which means when I'm talking to you about the complement of that, it's all the stuff outside that red area that I've shaded in, which gives me just this outside area, which is what we call region 4. If, on the other hand, I talk to you about A complement's all the stuff outside of A, which is all of this stuff from region 4, but it's also this stuff in here. And then if I talk to you about B complement, well, that's all the stuff outside of B, which is all of this stuff, as well as this, because this is outside of A, outside of B. Now I'm trying to find the intersection. That's the common ground. That's the place where I've got two different colors crossing themselves. And that's, again, all of this area here, which, as we said in our counting, is just region 4. So once again, I've used deductive logic to look at the general rules and come up with something that works for any particular set. So these are the different diagrams that I've got. These are the different rules I can use. So for set operations, I've got union, I've got intersection, and I've got complement. And then I also have the cardinality formula, which talks about counting things, and I also have the De Morgan laws. These are the tools you're going to use to solve the questions in this section of the book. One thing I want to point out about cardinality. In cardinality, we talk about finite sets. Finite sets just means that there's a very specific number of things. So when I talked about the number of people in the VC math department, I got out 5. That makes this a finite set. Some sets aren't finite. Some we call infinite. An infinite set that I've just already talked about when I was talking about capital letters is this one, the counting numbers. In a set, when I'm using the roster method and I use this triple dot here, that means continue on. Continue on in the obvious way. Not everything's obvious, so I have to be careful. For example, here's a set. If I say continue on in the obvious way, you know by looking at these that these are all the even numbers, so you know that we're going to put even numbers in this place. I could do one for the odd numbers as well. Here I've got all these whole numbers that are integers, and they're all the positive ones, so I know these are the natural numbers. And I would continue up 5, 6, 7, 8, 9, 10, and so on. These are examples of sets that are infinite. They don't end, which means if I try to talk to you about this, it doesn't make any sense. I don't know. Trying to spell ugh maybe? Ugh. This isn't something that you want to talk about really. Not in this class. It's an infinite set, and so we wouldn't do something like this. Don't do this. You can only use this cardinality counting process to talk about sets that have a definite ending. You know exactly how many things they have in them. Alright. There will be another video after this one for section talking about Venn diagrams and set operations in terms of how to solve them with word problems. And you're going to want to look at that before you attempt some of the homework.